So hello everybody. Welcome to the session of the Nečas Seminar on Continuum Mechanics. So today's speaker is Elvira Zappale from the University of Rome, Sapienza. So Elvira got her PhD in 2002 from the University of Naples, and then she was a assistant and associate professor at the University of Salerno. And I think in the pandemic time, at the end of 2020, she moved to Rome, and she's now associate professor at the Sapienza University. And she's an expert in calculus of variations, supremal problems, but also applied like mechanical problems, in particular structured deformation. And this is the topic of the seminar today. So, yeah, please.
Thank you very much for the invitation, for this very nice introduction. I apologize always for my voice, but I cannot do better than that, always. So I will describe a joint project that started a few times ago with Ana Cristina Barroso and José Matias, both from the University of Lisbon, Marco Morandotti at Politecnico di Torino, and David Owen at Carnegie Mellon. Well, actually, I have been introduced to these topics by them who were already working since a long time on this field. And that also because, as you could see from the title, I will talk about structured deformation, which is a field that has been introduced by Gian Pietro Del Piero and David Owen in last century, and in the end of last century, I would say. Well, okay. In fact, the plan of my talk is like that. First, I will describe some mechanical properties of this theory, the way it has been introduced actually by Del Piero and Owen, as I said. Then I will describe the variational formulation due to Choksi and Fonseca. Then I will move to this new theory by Luca Deseri and David Owen, who is named the hierarchical systems of structured deformation, and I will describe later what it's about. And finally, our contribution, which is, let's say, a variational formulation of this mechanical theory. Well, so what is a first-order structured deformation? Is a method, I would say, that Del Piero and Owen introduced, in the sense that they were considering a unified approach to describe all the possible contribution due to either microslip separation and classical deformation that might happen in a body. So the idea is that you want somehow to look at your body and trying to understand which part of your big deformation comes from something who was smooth at the micro level, something who even if it appears smooth at macro level, comes from something who was really, let's say, coming from some plastic effect or some fracture effect at the micro level. And then, well, so, I'm sorry, I did. So the point that Del Piero and Owen made was essentially this description. So you may have a simple deformation here, which is actually a pair, K and G, where K is essentially where your deformation field G is not smooth, essentially where you might have a fracture, let's say. And then they introduced the idea of limit of simple deformation. A limit of a simple deformation is indeed a tripole. And this tripole is, again, a set K and a field, the deformation, let's say, little g, and then there is another field that they symbolize with capital G. In the construction made by Del Piero and Owen, both these fields, little g and capital G, are bounded fields. And okay, this is limit in the sense that this tripole can be achieved in this way by a sequence of simple deformation in the sense described above. Namely, your set K is the set theoretical limit of some sets Kn living at micro levels, and the couple little g and capital G is achieved in this way. Essentially, the little g is achieved as limit of simple deformation Fn, and capital G is achieved as a weak limit of just the smooth part of your deformation gradient Fn. In fact, as I will clarify in a second, when I will use this symbol nabla, I mean just the smooth part of the distributional derivative of the field Fn. And then the point is that after this, let's say, limit description, they said that the structured deformation is essentially such a tripole K, little g and capital G, where Kg is a simple deformation, and the field capital G outside the set K is a measurable field, or it can even be considered as a measure achieved in the previous way. And also what they imposed is that there is a determinant constraint, namely that the determinant of the smooth part of the deformation gradient of little g is greater than the determinant of this metric field capital G, and this is everything is bigger than a positive constant n. Well, okay, the point is just to visualize why this introduction. I guess the idea that clarifies is this example, the so-called broken ramp. Namely, you can, in dimension 1, you can consider that your set omega is the interval 0, 1, and then you may see your field little g to be 2x, capital G to be the constant function 1, and k to be the empty set. So these both fields, capital G and little g, are achieved in the previous sense by as limits, simple deformation, which are these fields Fn. Clearly, okay, Fn, it is defined as to be x plus k over n, as you can see from the picture. So it is really easy to see that Fn uniformly converge to this little field little g, and then the absolutely continuous part of the derivative of Fn goes to capital G. And so you can see that indeed, if you consider the entire distributional derivative of Fn, its limit is different from the limit of its absolutely continuous part. So, and this will really, make really a distinction between these two fields, the absolutely continuous part of the derivative of little g and the capital G. The other example is this example in 2D, where the field little g is x1 plus x2, and then x2 as second component, and g is the identity matrix in the 2 by 2 identity matrix. And in the same way, exactly in the same example, you can approach this field little g and capital G in the way I described above, just working on the x2 variable. So the idea is indeed the one of a deck of cards, imagining that you have the number of your cards which increases as an. Well, okay. The point is that let's say this theory of the Pierre-Owen makes sense indeed, because whenever you take such a tripole k, little g and capital G, then you can achieve it as a limit of this deformation, and they prove this approximation theorem. And and the way one can describe such convergence is with this wiggle, this strange arrow, let's say this fancy arrow in red below. Well, The point is that, so let me describe again a little bit better from what I'm sorry, I did the wrong. So, okay, what happens, as I said, is that capital G takes into account just the smooth changes at micro level, while the field G takes into account, let's say, the entire deformation happening at micro level. Okay, so you can indeed, as in the example that was shown before, essentially realize that nabla G, so the absolutely continuous part of your deformation G, little g is different from capital G. And this difference is usually denoted in literature by M, and this M can be has been described by Owen and Paroni in the following way. At least you can see that the trace of this vector field capital M is obtained essentially as let's say a Radon-Nikodym derivative of the limit of the trace of the single part of the micro deformation Fn, because indeed by this bracket Fn I mean the difference between the two sides limit. I mean Fn plus and Fn minus. Let's say imagine that they are jumps, so that your Fn has different traces, and then nu is the normal to this set where you have discontinuity of your Fn. Well, okay, so after this description, okay, they also gave a mechanical description also about what is the positive part of this scalar product between Fn and nu, and the negative part. So one takes into account the separation and the other the switching. Well, okay. The point is that, as I said in the plan of my talk, I'm more interested in the variational formulation of this theory. In order to do that, I fix some notation, and the setting where this theory will be described is in the space of fields with bounded variation. So I will denote U, my field, which is in BB of omega and RD, and then I will use the following decomposition that was somehow hidden in what I was already saying before, that the distributional derivative of U, which is of course a vector valued measure, can be decomposed as an absolutely continuous part that I usually denote by nabla U, and then you might have, and then there is of course the singular part, which in turn can be decomposed as a jump part, so U tensor nu of U, and then the counterpart. Actually, for the theory made by the Pierre and Owen, we are not very much interested in this counterpart of this derivative, but then I will come to this. Maybe I will clarify what I mean by that later in the next slides. And so, what is important for that? I mean, the important point is that I want to somehow recast this description of the structured deformation in this BV setting. And why is this so useful? Because somehow I can associate the set K and the field G with the same field little u, if you like. So essentially, I will consider K to be the set where the part of the distributional gradient of u concentrates, neglecting the counterpart. So of course, really where I have the jump part of my distributional derivative of u. So everything will be recasted in a unique field. And then, of course, the field capital G will be any field that, according to the topological description of convergence that I will consider, can be either an LP field, an L1 field, or a measure more generally. So what is also very, very important, the other crucial part is that I have to be able to achieve, in the sense of the approximation theorem, let's say I have to describe a correspondent convergence in this new setting for every structured deformation. So it's important to make sure that an approximation theorem exists. And the crucial tool to prove that is this result by Alberti, a well-known result from last century, which essentially says that whenever you take an L1 field, this field can be considered always as to be the absolutely continuous part of the distributional derivative of a BB field F. And also, for what concerns the singular part of your derivative, what here I'm denoting by DSF, this can be controlled by the L1 norm of your field capital G, and the same holds for the L1 norm of F itself. Why is this result important? Because it is indeed the tool that has been used to prove the approximation theorem. So the approximation theorem in this variational formulation is due to Choksi and Fonseca, and the idea is essentially the following. You consider a couple, so little g, that, as I said, also encodes the set capital K as its singular set, and then a field capital G. Then you can find simple deformations that now will be SBB field themselves. So again, UN will be considered together with its jump set, J of UN. And what you can prove is that UN converges longly in L1 to little g, and the absolutely continuous part of the gradient of UN goes to capital G. The idea is that you fix your L1 field capital G and nabla G, little g, and you find by Alberti theorem a field H whose absolutely continuous part of the gradient is indeed this difference. And then you take a piecewise constant approximation of this H, and then you can see that you have the convergence that you want. So, I mean, the theory has already a good correspondence in this variational formulation. But I want to say something. The point is that as it was already shown by the examples, is that if you consider the entire derivative of your SBB field, your simple deformation UN, their gradients converge to the entire gradient of your field G, which means that the singular part, of course, by linearity, goes to the difference between nabla G and capital G. So that field that before was denoted by M. This is somehow essentially conflicting with the so-called SBVP setting by Luigi Ambrosio. So namely, what is important in this approximation is that to really have that your capital field G differs from nabla G is that you want that your singular set of the simple deformation, so SUN, essentially is getting an infinite length. Otherwise, you are obliged to have that nabla G is equal to capital G. So another thing before I go further about notation is that, okay, the couple little g and capital G will be denoted by SD of omega, so structured deformation, and the convergence now in the sense of this approximation theorem will be denoted by this alpha arrow with a star. I mean, okay, it should be quite clear. Then, what about the energetic description? Choksi and Fonseca made this formulation. They said that the energy that they want to associate to a structured deformation, capital G and little g and capital G, is nothing but the least possible in the variational setting energy that you can get from as a limit. So this here as a limit of the energy UN, where UN are simple deformation converging in the above sense to the couple little g and capital G. So the energy E of U has crucially two components. A part coming from, a bulk term, which is this W, depending on the absolutely continuous part of the deformation U, and the surface term that depends on the jump of your field U and on the norm. Well, okay, so something which is a surface, is an elliptic integral. Well, okay, the point, the interesting part in this description is that Choksi and Fonseca were able to describe the energy associated to a structured deformation, again proving that it has an integral form. This integral form is the one that I'm describing here. So is this this integral over omega and bulk term, depending on both the contribution. So let's say the absolutely continuous part of the gradient of G and capital G. And then there is a contribution due to the surface term that is denoted here by HPCF. Let me say something about this P and about this representation. So here, and most of the things that I will say later, I'm focusing on the case where P is bigger than 1, which means that some assumption will be imposed on the original energy densities W, in the sense that I will restrict my attention to fields capital G, which are LP fields, and the convergence that I will consider due to some coercivity imposed on this field W will be the weak LP convergence of the absolutely continuous part of the gradient of the simple deformation UN to capital G. Also, there is, so when here I say SDP of omega, I really mean that capital G is an LP field. Also, I'm automatically restricting this representation on SBV for what concerns the field little g. Namely, this field little g, in principle, can be a BB field. I mean, the convergence that the fields UN by compactness have are going to reach the entire space BB. We are now for some of my purposes, and especially for sake of exposition, I'm just focusing on little g, which are SBB field. So namely without counterpart in their distributional derivatives. But clearly this theory is possible. And also if the assumption on the convergence to the absolutely continuous part of the gradients of the approximant fields UN is due to the original form of the energy is the weak star, clearly could lead me to have a capital G, which is a measure and no longer an LP field. And also there might be an interaction also on, the way this energy density HPCF is. But this I will clarify now that I show the formulas. Okay, no, well, I will clarify it later now that I go to hierarchical system in order not to, what I'm doing, I'm going in wrong direction. Okay, now that I'm going to this new theory. Okay, so far I have described what happens to so-called first order structured deformation. What about this hierarchical system? This idea that Desari and Owen very well developed, I guess, a couple of years ago, is due to the, let's say, an analysis of the real system. Let's say either man-made objects or even natural system, which essentially exhibit several levels deformation and several levels of interaction. Even at macro level, you can see that there are some effects which are due to sub-macro level, other to sub-macro level, and so on. So they wanted to make clear this kind of interaction. And in the classical example that I guess helps a lot to clarify what I tried to say is this example of a bundle of papers. Essentially, you can see that you can realize that there are several levels of way of looking at this picture, in the sense that you can see that you may see it from far away, and it seems to be really like just the large stack containing all these sheets. Or you can see that there are several stacks, or you have several, let's say, bundled papers all together, or you can look at it from very close and you see that there are even several sheets which are, positioned in a different way, one from the other. So to describe these several effects, they tried to essentially expand on the theory of structured deformation. So somehow, one starting from that picture can focus on morally two level and one micro level. So you have the macroscopic level that I'm calling here level 0. You can have an intermediate submacroscopic level, level 1, and then you can see what happens from every single sheet. So with this level 2. And again, now you can see to the entire deformation at level 0 to be denoted by a field little g. But then you can see that there are more fields appearing than just capital G, that here I'm denoting by G1 and G2. They are all fields that you can detect at level, at the macro level, but they come from different approximations. So let's say something happening at the finest micro level, and something happening at the intermediate macro level. So somehow the same example that I was making before for the deck of cards can be made now here. So morally, you can consider three fields, say G1, G of x1 and x2 to be x1 plus mu0 x2 and then x2. Then you can define G1 as to be the identity matrix plus mu1, then the tensor product between mu1 and mu2, and the same for G2 with a different constant mu2. Clearly choosing appropriately mu0, mu1, and mu2, you have the accommodation inequality that is in this setting. So now the point is that you would like to see that this type of can be now achieved by limits in an appropriate sense of deformation occurring at this micro level and intermediate level. So if you look now at these two sub-levels, you can consider this sequence of simple deformation, a double indexed sequence Fn1, Fn2, defined in this way. Of course, also K and H are natural numbers between N1 and N2, and you can make exactly the same approximation that I was showing before for deck of cards. One are happening at level N1 and the other happening at level N2. So the innermost limit is the one which is taken first. So you first send N2 to infinity and then N1 to infinity. So what happens? That you can see that G is achieved as, as first the limit in N2 and then the limit in N1 of Fn1 and N2. And clearly the entire distributional gradient of Fn1 and 2 goes to distributional gradient of G. And then you can look at the smooth deformation gradient of these F1 and Fn1, Fn2, and then you can send the limits, first in N2 and then in N1, and this gives you the field capital G2. So you see at the macro level what is due to the smooth change at the micro level, let's say the level 2. Or you can consider something else. You first take the limit of your deformation in N2. So you pass from the micro level to the sub-macro level. You consider the absolutely continuous path. So let's say the smooth change of this intermediate deformation, and then you consider the limit as N1 goes to infinity, and you achieve your field G1. So, okay, and then as it happens in that example, Design and Owen proves that here, okay, the 2 below HSD2 means that I am considering a 3-level hierarchy, so level 0, level 1, level 2, is achieved in the way I was saying before. So, well, okay, let me, okay, this I guess is what I was describing already in the examples, but again, you can somehow, as it has been done in the classical theory of structured deformation, you can consider the difference between nabla G and capital G and denote that field by capital M. And this difference between nabla G and G1 or G2 and G1 can have a mechanical description in terms of other fields, M1 and M2, let's say. Okay, well, what is now, I mean, which was our first contribution, is the following. Can we achieve in this same way, essentially taking iterative limit, first as N2 and then as N1 going to infinity, this triple little g, G1 and G2? The answer is yes, and in the sense that is described here. So for little g, you have L1 convergence. For G1, you consider as far as G1 is a measure, you have a weak star convergence of the limit, sorry, of the gradient of the limit as N2 goes to infinity of UN1 and N2, which here I'm calling GN1. And then you can consider the weak limit of the smooth part of the gradient of UN1 and N2, going to this G2. So this, let's say, this convergence has, I mean, can be really easily described in this way, even in this SBV and measure setting, times measure setting, and also an approximation theorem can be proven. And the fact is that whenever you take a triple G, G1, and G2, this can be achieved as the limit in the sense of that has been described in the previous slide of this deformation UN1 and N2, which is the idea. The idea is essentially to apply repeatedly the same construction that I was doing for simple structured deformation. So essentially considering applying Alberti's theorem to every difference between, so between nabla G and G1, and then between G2 and G1 with these fields HK, and then a piecewise constant approximation of those. Here, for simplicity, I'm stopping my description to 3 level, but clearly you can describe more levels of hierarchical systems. Okay, here is the description and let's say the proof of this result, which is pretty, I mean, automatic. So clearly you have that the double limit of UN1 and 2 is indeed your field G because of the way you have chosen HK and H bar and K. And the same happens essentially for the gradients, the absolutely continuous part of the gradients directly at the level, at the micro level or at the intermediate level. So well, then there is another observation that for our purposes we found useful, which is the following. Namely, you can consider triple little g, G1 and G2 as a higher 3-level a system, a hierarchical system with 3 levels, so G, G1, and G2, and you can see the following. You can first consider just the couple G and G1. It is in itself a structured deformation in the sense of Choksi-Fonseca, let's say. Because of that, you can find a sequence that here I'm denoting by little gamma n1 and capital gamma n1 that converges to G and G1 in sense of structured deformation. On the other hand, your field G2 is a measure, or if you are in LP, is an LP field or an N1 field, whatever you want to focus on. And this can be achieved by weakly by a sequence gamma n1 of fields which are maybe as it is here LP fields. Then, so because of that, now you are left with such couple, little gamma n1, which are SBB fields, and capital gamma n1, which are LP fields. So somehow this couple, little gamma n1 and capital gamma n1, are structured deformation themselves. So they can be achieved again in sense of Choksi-Fonseca as limit of structured deformation. So this is an equivalent way of proving that this triple, little g, G1, can be achieved by the repeated limit UN1 and UN2. So somehow applying twice the construction made by Choksi and Fonseca. Okay, here is what I was already describing in words. This is the idea that, how the fields UN1 and UN2 arise from little gamma n1 and gamma, and capital gamma n1, and this is the convergence. Well, okay. The point is that now it comes the energetic formulation. What about the energetic formulation? So the idea is, there are several ideas. One is somehow to make the analogous formulation than the one made by Choksi and Fonseca. So considering that the energy associated to a triple little g, capital G1 and G2 to be the most economical way of obtaining it as a limit of energies of simple deformation. So this energy E of U that now will be taken as a repeated limit first in N2, then in N1, and then infimizing on all the possible sequences U and 1 and 2 converging indeed to this triple. Okay, this is one possibility. And the point is that this is a good choice. And in fact, here, again, I'm stopping to the case of a 3-level system. You can see, because of this second way that I was proposing to you about the approximation theorem, you can see that this energy IP indeed coincides with this one. So namely, first you define an energy IP tilde obtained in this way. So essentially as the variational limit of the energy I of Choksi-Fonseca. So let me say the following. You start with the energy to a simple deformation, this E of this Vn2. This generates, in the way that I was describing before, the energy by Choksi-Fonseca. You take this energy to be the one that you consider as your starting point to define your energy IP tilde. And you can see, because of the approximation theorem, that the energy that was in the, 2 slides ago, IP coincides with this IP tilde. And this is a very useful, at least for our point of view, consideration, in the sense that IP tilde is achieved really as a repeated limit, variational limit. So it has all the nice property to be a measure. You can represent it with respect to the most relevant measures, which are again the BB measure associated with your deformation gradient G, and then the L1 and P measure G1 and G2. Good. So then the representation formula comes, and it is the following. This representation formula here has in the bulk energy, I'm considering again P bigger than 1. That's why there is a P as an index, let's say, in my formulas, as a bulk density, which now depends explicitly on the absolutely continuous part of the gradient of your deformation G, on capital G1 and capital G2. And then you have a surface term, which is depending just on your field G, little g. Indeed, it is concentrated where G has its jump in its singular state. And also, your density HP can be represented as a minimum problem depending on the original energies, not really the original energies, but the one which comes from Choksi-Fonseca expression. So this is this infinitization of this HPCF and the little HCF, requiring what? Essentially, you are convexifying at the same time as other operation on your variable C, so what takes into account G2, let's say. In fact, you are optimizing on the possible fields capital gamma, and then you are considering the classical approach for structured deformation. So you require that you are minimizing all the fields U in SBB of omega, such that they have their fine boundary datum on the unit cube Q, and their average is indeed your constant B. The other important observation is that for the case P bigger than 1, the surface energy density coincides with the one by Choksi-Fonseca. So morally, no other operation is indeed necessary. And okay, let me say what I was saying, what I was skipping at the beginning, in TAR, which is the following. In TAR, also this Choksi-Fonseca density, this capital H CFP, can be achieved by a minimization formula depending on W and psi, where I recall you that W and psi are the energy density as your original formulation. So the energy E. Well, and this an analogous, I mean, not an analogous formula, but kind of SBB elliptic envelope is what describes the energy density HPCF. So you are minimizing all the possible SBB fields, which coincides with the jump function 0 lambda on the cube, which has one side parallel to nu, and which are all the fields which are piecewise, I mean, piecewise constant, let's say. Okay, then I'm not entering in details about the proof, but okay, the arguments are the one via Brevard. I also would like to say that the assumptions that we are making are the same as the one that are somehow common on this in this description. So unfortunately, there is no possibility so far for our knowledge to consider determinant constraints. And also we have some technical assumptions which are not really nice, but this was what we could do so far. So somehow we are considering that the original energy bulk density W has some P coercivity. That these assumptions are that so far we could not remove. And then there are these other assumption I want to remark is that the surface field psi may have an X dependence, okay, as also the fields W, but it's not that. What I wanted to make is that it does not control the length of the surface measure, if you like, of your jump set, but just the amplitude of your jump. And then it is subadditive, positively homogeneous, and so on. Okay, the point, do I have, how much time do I have? Can I, it's already, I'm already out, maybe. Okay, can I? Okay, thank you. So let me say the following, which then was let's say what gave us another possible idea of defining energies, which is this one. Okay, the field HP inherits not the field, the density capital HP inherits some properties from the previous field HPCF capital and small. Well, and in fact, the point is that they behave somehow in the same way, in some cases even more regularly than the original ones. And this is somehow, this gave us another possible idea, which is the following. Essentially, it came from this example made by Shirawi in 2017, which morally helped to understand, give precise expressions of these densities, HPCF or HP in other contexts. So if you start by an original bulk density, W, that here I'm calling W0, so the one that you put at the level of your energy E, and you consider a surface energy, which is just the trace of your singular, your jump part of the derivative, so the scalar product between lambda and the normal, you can see that the above formula gave you at the first step a bulk density W1, which is nothing but W0 plus the trace of the difference between A1 and B1. So let's say B1 is your capital field G and A1 is your nabla G. And psi1 is equal to psi0, so it stays the same. So in this way, you can keep going to any level of structure, of a hierarchical structure deformation, and you can get this nice description. So the idea was somehow this idea of going could be performed again in the way we can define the energy associated to a hierarchical system of structured deformation. So let me say just something. What I'm doing, I'm going in the opposite direction of what I wanted to say. So let me come to this slide here. What is the point? The point was that, okay, this is the formula that we have achieved in our description. We could do the following. We could, after the second step, we could freeze the variable C. So take it as a constant. And what we get is that we get the field HP, which depends on A and B. But already this is, no, I'm sorry, I'm confusing you. Let me say again because I said something wrong. Okay, at the first step in our relaxation, we get HPCF. This depends on the gradient of U and this field gamma. Okay, what's the point? If we fix the field gamma, we take it as to be constant. What we have is that we have a bulk density which depends just on the gradient and the surface density which has the same form as the one that in original energy E. Then we can relax at the Choksi-Fonseca. And then after this relaxation, we get dependence on two new fields. And then after we have done that, we replace the constant value C by another field G2. And this can be done at any stage. This construction is apparently, okay, it's of course higher than the energetical construction that I was presenting before, but it has the advantage that it's very clear to understand the formulas that we get at each step. And so far, we don't have a precise example showing that it is in general really strictly higher than the energetical description I made before. Finally, And then with this I will stop. The point is also that in principle, it is possible to consider 2 or L level, 3 or L minus 1 level of structure, L plus 1 level of structured deformation. So G1 up to GL, and then saying that, okay, if I have a functional which depends on this hierarchical system, and then depends on the set omega, open set omega, where I am considering this deformation occurring, and I assume some natural assumption, so morally that my fields capital F is the restriction of another measure. It is lower semi-continuous with respect to the natural convergence that were arising before. So the L1s from convergence for the Gn to G, and the weak convergence for at each field Gi from approaching field Gin. So my energy is lower semi-continuous. I have some locality properties here, so namely whenever little g coincides with u and capital Gi coincides with fields ui, the energies are the same. And also I have some control from above in terms of the total variation of G and of the LP norm of the Gi. Okay, I have the power P of the LP norm, and with some coercivity assumption, this is again a technical assumption, then it is possible to describe this functional calligraphic F as an integral. In which way? Not really taking directly the Nikodym derivative of this object calligraphic F, but infimizing this energy calligraphic F on all the possible fields which coincide with G on the boundary of any open set A, whose average, and then infimizing all the possible fields ui who has the same average as Gi in A, and then taking the Radon-Nikodym derivative of these fields little m. This gives you, with respect, Radon-Nikodym derivative with respect to the Lebesgue measure gives you, sorry, okay, I made a mistake, gives you an energy density bulk F and the surface psi, and you represent. There is, okay, the representation is very well proved when P is equal to 1, and there are some technicalities and some restriction due in the case where P is bigger than 1. So namely, the fields capital G and Gi have to be L infinity. This is a restriction for this theoretical approach, but it is not for the description of our relaxed functional. Sorry if I took a lot of time, and I apologize because I'm not able to put the right symbol to say thank you on your read because I don't know check. So thank you very much, and sorry for